In the sunlit hills of southern France, a colossus is rising. This isn't the work of a single nation but a global collaboration of unprecedented scale, uniting 35 countries in a shared mission. This is ITER, the International Thermonuclear Experimental Reactor. It's a sprawling city of science dedicated to one of the most ambitious quests ever undertaken. The goal is simple to state, yet profound to achieve. Harness the same energy that makes our sun shine. In the heart of every star, immense gravitational pressure squeezes hydrogen atoms together so tightly that they fuse, forging helium. In that moment of fusion, a tiny fraction of their mass transforms into a brilliant burst of pure energy. This is Einstein's famous equation in action, E equals mc squared. That energy crosses 93 million miles of empty space, warming our world and powering all life as we know it. For centuries, our own progress was fueled by a different kind of fire. We burned wood, coal, oil, and gas to build our civilization. But this chemical fire, the engine of our modern world, has come with a heavy price. The cost is unsustainable. Greenhouse gases, a warming planet, rising seas, and extreme weather. We stand at a crossroads facing a challenge that will define our future. We need a new fire, a new way forward. Fusion offers that new path. It promises a source of power that is clean, fundamentally safe, and fueled by a resource that is virtually inexhaustible. Its primary fuel, an isotope of hydrogen called deuterium, can be easily extracted from ordinary seawater. The amount in a single bathtub could provide a lifetime of electricity for one person. Unlike fossil fuels, fusion's main byproduct is harmless helium. And unlike nuclear fission, there is no risk of a meltdown and no long-lived radioactive waste. Imagine meeting our energy needs without compromising the health of our planet. This dream, whispered for decades in laboratories around the world, is now being forged in steel and concrete. On Earth, we can't use gravity to contain this power, so we must build an invisible cage. Coils of superconducting wire, some of the most powerful magnets ever conceived, will hold a star-shaped flame. We are building an artificial star, a tokamak here, in our own backyard. It is a monumental feat of engineering, a cathedral to science. This endeavor elevates our perspective from the terrestrial to the cosmic. We are the generation that has begun to build a star on Earth. It is more than just a scientific experiment. It's a statement of hope, a legacy that could reshape human civilization and our relationship with the planet. So, how do you build a star in a box? In the sun's core, immense gravitational pressure forces hydrogen atoms to fuse. Here on Earth, we can't replicate that cosmic squeeze. So instead of gravity, we use extreme, unimaginable heat to overcome the natural repulsion between atomic nuclei and force them together. At the heart of ITER is a device called a tokamak, a Russian acronym for toroidal chamber with magnetic coils. It's a colossal hollow donut, a vacuum chamber so empty it rivals deep space. This near-perfect vacuum is critical, ensuring no stray particles interfere with the delicate process about to unfold. Into this chamber, scientists inject a few grams of hydrogen fuel, its heavier isotopes, deuterium and tritium. Then, using powerful microwaves and particle beams, they heat it to an astonishing 150 million degrees Celsius, 10 times hotter than the sun's core. At that temperature, gas becomes plasma, a turbulent cloud of charged particles. If plasma touches the walls, it cools, and the reaction stops. The elegant solution is an invisible magnetic cage, generated by colossal superconducting magnets. To work, these coils are cooled to minus 269 degrees Celsius, creating a mind-boggling paradox. The hottest place in the solar system, meters from one of the coldest. These fields trap and suspend the searing plasma, preventing it from touching anything, a cosmic ballet of precision, holding a small piece of a star on Earth. When people hear nuclear, they think of fission. Fusion is fundamentally different. Not splitting heavy atoms but joining light ones. Deuterium from seawater and tritium bred from lithium can fuel the reaction. Fusion makes helium and energy, no greenhouse emissions, no long-lived high-level waste, and crucially the process is inherently safe. Fusion is incredibly delicate. Any disturbance and the plasma instantly cools and the reaction stops. A runaway chain reaction is physically impossible. Clean, safe, abundant, the holy grail of energy. ITER itself will not generate electricity for the grid. Its mission is scientific, to prove we can get significantly more energy out of the reaction than we put in, a goal known as net energy gain. The data gathered here will be the blueprint to design the world's first commercial fusion power plants. The science is hard. The payoff could transform how we power the world. ITER's primary goal is to achieve a burning plasma, a state where the reaction is largely self-sustaining. It aims for 500 megawatts of thermal power from just 50 in, a historic tenfold return. This would be the first time a fusion device produces a massive net energy gain, proving the principle of a future power plant. But containing a star on Earth is a monumental task. Inside, plasma will rage at 150 million degrees Celsius. Taming its wild turbulence and perfecting the magnetic confinement that holds it are challenges at the very edge of our scientific understanding. Every component, from the massive vacuum vessel to the tungsten diverter, demands unprecedented precision. These materials must survive a relentless assault of extreme heat, pressure, and intense neutron radiation, a feat of engineering never before attempted on this scale. This is also a deeply human endeavor, one of the most complex international collaborations ever. 35 nations, including the European Union, China, India, Japan, South Korea, Russia, and the United States, are working together. In an era of division and short-term thinking, ITR is a powerful symbol of unity. First superheated plasma experiments are scheduled in the coming years, the moment this machine truly comes to life. Success is not guaranteed, but the attempt itself is a profound statement of hope, an investment in a future we are determined to build. The power unlocked in France could light our cities and desalinate our water. It could even fuel our journeys to other worlds. This is our cathedral moment, a bold gamble for the ages. If we succeed, we will gift a cleaner, safer, everlasting power, a brighter future powered by the fire of the stars. Our journey through the cosmos is just beginning.